Today we are going to talk about bending of plates. We have already studied bending of beams, bending of curved beams. We will now like to see if the component is like a plate. It could be in the form of rectangular plates, it could be in the form of circular plates. When they are subjected to transverse loading, how do they undergo deformation, and at the same time how stresses develop. That is what we are going to study today. Let us consider a rectangular plate which is very thin, the height is small compared to length or the width. When you try to apply bending load to such a plate, let us say we apply the bending load in the xz plane like this, and we would like to indicate this moment by mx. So, when you do that, what you find is that we are trying to have bending generated like this, the surface should have curvature like that, and you find that because of that curvature, you are going to get some radius of curvature here in this direction. While you are having this curvature, you can appreciate that we will have tensile stresses at the bottom of the plate and compressive stresses at this top fiber. So, compressive at the top fiber and tensile stresses at the bottom fiber. When the plate dimension here is substantial, what you find that when it is trying to get stretched at the bottom fiber in the direction perpendicular, in this direction there will be contraction, and since there is compressive at the top fiber, in this direction there will be extension in the direction at the top. So, therefore, you see that you get contraction at the bottom fiber here in this direction. So, therefore, you are going to get contraction here and the top fiber is going to get now stretched. Because of this, you find that the edges of the plate gets a curvature like this, it does not remain straight. So, you have tension stresses there and compressive stresses there. So, it gets actually fold or rather bend like that. So, there is a curvature demonstrated by the plate towards the edges, and this curvature gradually dies down as we move towards the center of the plate. And we can find out this curvature very easily if you consider that the bending is producing a strain, let us say epsilon x. So, because of this I have the bending strain which is z by r. So, thereby meaning that for positive value of z we are going to have positive strain, and we try to consider that this x axis is right at the center of the plate or xy plane coincides with the center of the plate, and then we have this as the distribution of the strain. So, what we are trying to say that this is the height, let us say this is the height h, then we have a strain distribution which is linear. So, if we consider epsilon x to be plotted in this direction, so this is my x axis. So, then in that case I am going to get tensile strain here, compressive strain there. So, therefore, I have this compressive strain and tensile strain at the bottom. Now, the strain which is going to develop because of the strain in the x direction, and that is going to develop in the y direction, it is going to be nu times the strain in this direction. So, therefore, we can write this thing as epsilon y is equal to minus nu z by r, which you can write as minus z by r by nu. So, therefore, you find that this is a curvature. So, this is again another curvature, this curvature r by nu we call it anticlastic curvature. So, it is known as anti anticlastic curvature. So, this radius of curvature, that is C at the edges, is going to be of value r by mu. So, what you find here, that as you consider an element on the surface of the plate, you find that there will be stresses in the x direction, there will also be stresses in the y direction. Now, this tendency of curving like this is prevented towards the center of the plate. So, there is no such curving at the center of the plate, and you find that these stresses are going to actually come up here in the y direction as well. So, what you find that an element of this type So, if we draw that element, we will have the scale here, this element is going to be subjected to stresses in the x direction. It is also going to be subjected to stresses in the y direction. So, it is no longer a case of unidirectional loading as in the case of beam bending. In the case of beam bending, you have noted that the stress sigma y was 0. Now, the stresses are acting in the plane of the element, and therefore, it is generally considered to be two dimensional problem, and we can now write, since there are two strains, we can write sigma x, it is a plane stress sort of situation. So, we can write now sigma x is equal to epsilon x plus nu times epsilon y. So, that is the expression for the stress sigma x. Now, we have already mentioned that this tendency of anticlastic curvature appearing is not there towards the center, and towards the center you find that the stretching of the plate or contraction of the plate in the y direction is 0. So, therefore, epsilon y is 0, and hence we get the stress to be equal to E by 1 minus nu square into epsilon x, and since epsilon x is equal to z by r. So, therefore, sigma x is equal to E by 1 minus nu square into z by r. So, therefore, this term is getting knocked out. Now, if I try to consider, since the stresses are varying in the z direction, I can find out what is the moment produced by these distributed stresses on this edge per unit length in this direction. So, we can now consider that, let us consider unit length in this direction and height is h. So, what we get is that moment produced. So, we have sigma x finally is equal to E z by r into 1 minus nu square. So, if I want to calculate the moment produced per unit length in the y direction, then that moment we indicate by mx. This is going to be therefore given by integration of sigma x multiplied by 1 into dz into z. So, integration of this quantity will give us the moment per unit length. So, this is a simple integration. So, once we substitute the value, it come out to it takes the form z square dz, and which is simple integration and therefore, we have EH cube by 12 into 1 minus nu square into r. You remember in the case of beam, we had mx is equal to E by r into I. So, we have similar expression here that mx is equal to E by r into this quantity, which is nothing but I, which is equivalent to I. See, you have a plate of height 1 and width is 1. So, therefore, the moment of inertia should have been Bh cube by 12. So, 1 into h cube by 12. So, 1 into h cube by 12, that is what is in the case of beam, but then here we have an extra effect which is due to the plate action, which is 1 minus nu square. And this quantity we try to write like this: mx is equal to EH cube 12 into 1 minus nu square into r, and we write this thing as d by r, where d is equivalent to E into I and d is equal to E h cube 12 into 1 minus nu square, and this is known as plate stiffness modulus of rigidity. So, let us just have something to consider here. If I had a beam like this is 1 and this height is h, and we are trying to apply bending moment like this. So, if we apply bending moment like this, then in that case you certainly would have this d as d for this case is nothing but E into I, which is E h cube by 12. But on the other hand, if this is a part of a plate, then in that case we find that these faces are not free of any stress, and the plate gets extra rigidity. And in the case of a plate, so this is beam, and in the case of a plate we get extra rigidity, and this d is now equal to E h cube by 12 into 1 minus nu square. So, there is Poisson's ratio is always less than 1, and therefore, you get extra rigidity, and that is due to the fact that if you had the beam, this beam would have bent like this, it would have taken a shape it would have taken a shape like this, and there would have been anticlastic curvature. But in the case of, so this is again for the case of beam, but in the case of plate what we see is that this does not happen, it just gets bent So, it gets bent like this. This is the case of plate element, and that anticlastic curvature is prevented, and that is why there is some extra rigidity. There are, this face is now stress free, whereas in the case of plates they are not stress free, and this is the reason for getting this extra rigidity. Now, with this we can go ahead and in deriving the moment curvature relationship in the case of rectangular plates. So, we have considered loading about one axis of the plate, we could as well have loading about both the axes. So, let us now consider bending about both the axes. So, we consider a plate like this, these are our axes, and this is as if the central plane of the plate, we are applying mx bending moment, and this mx is per unit length. So, generally its unit will be Newton meter per meter. Similarly, my we apply in that direction, which is again having unit Newton meter per meter. So, we can now write, if the curvature due to M1, let us say that we have curvature equal to R1, and the curvature that we get in this direction is equal to, let us say, R2, then we can write the strain in the x direction is equal to Z by R1, and similarly epsilon y is nothing but Z by R2. And hence we can now write, it is a plane stress problem, and therefore we can write epsilon sigma x is equal to E z 1 minus nu square 1 plus R 1 plus nu by R 2, and similarly we can write sigma y equal to E z 1 minus nu square 1 by R 2 plus nu by R 1. So, it is nothing but sigma x is equal to E by 1 minus nu square into epsilon x plus nu times epsilon y. Similarly, sigma y is equal to E by 1 minus nu square into epsilon y plus nu times epsilon x. Now, we can calculate the moment per unit length in the x direction or in the x plane So, we will have moment in the x plane is nothing but minus h by 2 plus h by 2 sigma x into z dz, and this will give us E h cube by 12 into 1 minus nu square 1 by R 1 plus 1 by R 2, and this is nothing but, if we represent this quantity by as modulus of rigidity d, then this is nothing but 1 by R 1 plus nu times 1 by R 2, and by similar consideration we can write Now, My is equal to d into 1 by R2 plus nu times 1 by R1. So, these are the two moment curvature relations. Now, because of our coordinates, we have the coordinates, we have selected the coordinates which is like this. In fact, our x axis is like this, y is directed like this, and z is in this direction. So, therefore, these are the three axes, and the plate is curving in the negative z direction. So, that is what we have considered to be positive, it is not doing like this, and therefore, we would have the relationship between the curvature and the radius of curvature will be given by, for small deformation, 1 by R1 is equal to delta 2 W delta x square. So, what is we are going to have is that our this is what is R1, and since the deflection is here in this direction and this is x. So, therefore, you get double derivative of this deflection W with respect to x, that gives you 1 by R1. Similarly, 1 by R2 is equal to minus delta 2 W delta y square. So, finally, if we substitute all this, we find that minus mx by d, we can consider it to be, let us say, minus m1 by d is equal to delta 2 W delta x square plus nu times delta 2 W delta y square. Similarly, we can write minus my by d is equal to minus m2 by d is equal to delta 2 W delta y square plus nu times delta 2 W delta x square. So, these are the moment curvature relations. So, you had the relations in the case of beam bending, it was m by mx by I minus mx by I was nothing but delta 2 W delta x square, but in the case of plates you are going to get involvement of the other curvature as well. Now, for the simple case, if you consider the situation like this, if m1 equal to m2 and let us say that is equal to m, then you will find that R1 is equal to R2 and let us say that is equal to R, then we will have 1 by R is equal to minus m by d into 1 plus nu. So, for the symmetric deformation around the center point, you are going to see this sort of relationship. Now, let us see one simple problem. thermal let us consider a plate and let us see that if I have a temperature differential between the two faces of the plate, between the top and the bottom, let us say the temperature differential, this is maintained at 0 and this face is having a temperature of delta T, and therefore, the temperature is varying from 0 to delta T, and hence with respect to the center this is at minus delta T by 2 and this is at plus delta T by 2. And let us consider that height is equal to h and material constants are E and alpha, and of course, we will also have the Poisson's ratio nu. Now, if I do this, then the plate will undergo strain in both the directions without any distortion. So, if you consider that this is the plate and this is your y direction, then we are going to get the strain here at the top, it is going to be let us say in the x direction, and that is going to be nothing but minus alpha delta T by 2. And similarly, in this direction also we are going to get same strain. So, epsilon x epsilon y is equal to minus delta T by 2. So, that is at z is equal to minus h by 2. Now, from the relationship that we have got, that sigma x is nothing but E by 1 minus nu square into epsilon x. So, it is minus alpha delta T by 2 plus nu times minus alpha delta T by 2, and therefore, what we find is that this is nothing but minus E alpha delta T, this 1 plus nu will cancel and therefore, we will be left with 1 minus nu. So, this is the stress that is going to be at z is equal to minus h by 2. So, look at this, if we have raised the temperature here, then in that case this is going to expand and this is going to have because of this expansion it is going to contract. So, it will be actually trying to contract there, and therefore, we are going to have a stress of this magnitude. So, the stress is going to be of this magnitude. Now, let us try to consider more useful examples which we come across in very often in pressure vessels. So, in the case of pressure vessels, you will find that ends of the pressure vessels are going to be made up of plates like component, and then under the action of the internal pressure they are going to be subjected to transverse loading. So, we would like to look into such problems in the next portion of this particular lecture, and also will continue probably in the next lecture. So, now if we consider that plate is like this and it is subjected to bending, let us say all over the circumference of certain intensity, constant intensity. So, under the action of this bending, you will find that the plate is going to take shape like this, it will become curved like this. So, this is going to curve this way and this radius is going to curve this way. And if you now consider a strip near the center, it is going to get bent like this. Now, let us see what are the curvatures here. So, if we consider now a portion, let us say we consider a portion between this point and this point of the plate, which was initially horizontal, it has now got rotated and this is going to actually give rise to deformation like this in this direction. So, if we consider now the curvature which is going to come up here because of this d phi, let us say we consider an element at a distance of angular disposition, let us say phi, then this is d phi, then we will have some curvature coming up. This curvature where this angle is d phi and this curvature, let us say this curvature which is demonstrated here, let us say this is equal to r1, and this curvature is going to be given by rate of change of angle with arc d phi ds. Now, other curvature, so this curvature is going to be in this direction. We are going to also have one curvature in that direction, and that is we consider that curvature to be R2, and that curvature we can calculate. You see here that this particular section was initially vertical. So, therefore, at a distance x we had this section, it was vertical. Now, it has taken an angular orientation of phi. So, we can write now that x, if the curvature is equal to, let us say this portion has taken a curvature equal to R2, then this x is nothing but R2 sin phi. And since the plate deformation is very small, this angle is going to be, this radius of curvature is going to be very large and this angle is very small. So, therefore, we can write this thing as well as approximately equal to R2 into phi. So, therefore, this curvature is nothing but 1 by R2 is equal to phi by x. That is the second curvature. So, we have got now both the principal curvature of an element of the plate which is located somewhere here. So, we have taken the point A and let us say that this is the point B, and the center of curvature for this portion is O, where the center of curvature in the plane xy plane, I beg pardon, xz plane is nothing but this R1, that center is somewhere here and which is made by this radial line and that radial line. So, we have got the two curvatures. So, with this definition, it is now possible to go in for writing the equilibrium equation for the case of circular plate element. So, let us now consider a portion of the plate and its loading, and let us say that we have the loading which could be transverse loading on the plate or it could be some bending moment acting on the plate. Now, let us confine ourselves to a portion of the plate very close to the, it need not be close, I am sorry, it can be anywhere located over the plate, and let us consider an element which is like this. So, this is the portion of the plate that we would like to focus our attention, and we will consider now our radial directions to be x, and then this element is symmetrically placed about the x axis, and let us say that it is making an angle of d theta at the center. So, this is our z axis. Now, bending moment is not going to remain constant in general, and therefore, let us consider that on this face, theta face, which is perpendicular to, I am sorry, radial face, this is radial direction. So, this face is perpendicular to the radial direction. So, on this radial direction, let us consider that moment per unit length of the circumference is equal to m1 acting here, and this bending moment as we move to the other end, which is at a distance of, let us say, delta x from the first one. So, let us say that this is dx and this location is x. So, now here we are going to get some bending moment per unit length of the circumference. It need not be same as the other one. So, we can expect a change in the value of the bending moment to have a general situation. We can write now the bending moment per unit length here m1 plus dm1 dx into dx at this face. Similarly, we can consider now the bending moment per unit length here in the theta phase, which we will try to consider m2 per unit length, and for the case of axisymmetric loading, if you have the bending moment per unit length here m2, we would expect the same thing to remain here. So, this is m2. So, therefore, for an axisymmetric loading, we are going to get the bending moment to be disposed like this or coming up like this. Now, there can be shear forces. So, we can now consider on this face that shear force is equal to V, and the shear force which is going to come up on this face is equal to V plus dV dx into dx. So, that is the shear force. So, these are the loading, and of course, we can have our external loading, which could be like this, and the center of the this dx, a point let us consider A. So, now if these are the forces acting on the plate element, it must be in equilibrium, and let us see what we get by considering the equilibrium of this element under the action of the various forces. So, we have got all the forces acting on the element. Now, can you just think about what about the shear forces coming up on these faces? There can't be any shear force coming on these faces, because the moment is not varying in the theta direction, and therefore, there cannot be any shear deformation of these radial faces. The radial plane will remain always radial, and therefore, there is no shear deformation. Now, let us consider the moment of all the forces about the center point of this element, which is of dimension d theta and dx. So, we will consider now moment of all the forces which are shown here about A, that is equal to 0. And now, first of all, let us consider this moment, let us say that that is positive, and it is m plus dm1 dx into dx acting over a distance of x plus dx into d theta, and of course height if we consider to be unity, that will be also possible. So, we can now write m1 plus dm1 dx into dx x plus dx into d theta. I would like to repeat this point. This is the moment intensity per unit length of circumference. This is the length of the circumference. So, therefore, we do not need this height. We can get the total moment coming from this edge by this expression, and the moment which is counteracting that is nothing but m1 multiplied by x d theta. These are the two contributions. Then we have, see, this m2, if I show it as a vector. So, this vector, if I consider this face, it is like this, and the other face is exactly oriented like this, and this is my x direction. This angle is d theta by 2, this is also d theta by 2. This m2 we can show it as a moment vector like this. So, this is the moment vector, and therefore, this is m2 into dx, total moment vector is nothing but that. Similarly, in this direction we have total moment is nothing but m2 into dx. Now, we are trying to look for the component in this direction, and therefore, you see it is going to give rise to component like this in this direction, and which is, if this is positive, then the moment that will come out of these two will be like this, it will be directed like this, it will be like this. So, also for this one we are going to get contribution like this. So, this is m2 dx sin d theta by 2 acting like this, which is then opposite. So, it is negative. Similarly, for this also m2 dx sin d theta by 2 negative. So, therefore, both are additive. So, we will have minus 2 times m2 dx sin d theta by 2, and then we will get the moment of this about this point. So, also moment of this v about this point. So, if we consider first this one, it is nothing but v plus dv dx dx, and that is the intensity, and then momentum is nothing but, we have the momentum, of course, this the distance over which it is acting is nothing but x plus dx into d theta. So, into x plus dx into d theta, and the moment arm is nothing but dx by 2, and similarly for this one it is v, and it is producing a moment which is going to be same sense as this one. So, therefore, v x d theta, that is the total force due to the shear force, and its moment arm is dx by 2. So, that is the sum total of all the contributions. Now, if I see the cancellation, this is going to cancel with this product, and now if we just consider the terms which are linear in dx and d theta, then all the terms that will be remaining are the following: x dx d theta plus m1 dx d theta minus m2 dx d theta. We write this thing approximately equal to d theta by 2. So, that will give us this expression, and then here we have v x dx d theta equal to 0. So, this is neglecting terms with dx square d theta square. We have also had the pressure. If this is the pressure P, now that pressure will be distributed all over the plate and its centroid will pass through the point A, therefore, there will not be any contribution of the pressure distribution towards the moment, that is why we have not incorporated in this expression. So, finally, if we do the cancellation of dx d theta which is common, then we have dm1 dx x plus m1 minus m2 plus Vx is equal to 0. So, this is the equation which relates the moment to the shear forces in the case of a plate. We can make the substitution for m1 in terms of the curvature terms r1 and r2. So, we can now write. Before I do that, I would like you to again get back to this sketch here. In this sketch, we have shown that this is the curvature in the plane. If you consider that this is z direction, so this is z direction. So, in the xz plane, we are considering the curvature to be r1, and in the this is y direction. So, therefore, in the yz plane, the curvature is r2. So, this is the curvature r2 which is phi by x, and this curvature r1 is nothing but, if this portion is ds and this angle is d theta d phi, then d phi ds. So, we have already got those. So, now let us write m1 is equal to d 1 by r1 plus r2, which is nothing but, since 1 by r1 is d phi dx plus r2 is 1 by r2 is phi by x. So, therefore, this is nu phi by x. Nu is nothing but Poisson's ratio, and therefore, this d is equal to Eh cube by 12 into 1 minus nu square. Similarly, we can write now m2 is equal to d 1 by r2 plus nu by r1, this is nothing but d phi by x plus nu d phi dx. So, we can now substitute these expressions for m1 and m2 in the moment shear force relationship, and therefore, we have now x dm1 dx, it gives us d2 phi dx square plus nu times. So, we have to take the derivative of this with respect to x. So, it is nu by x d phi dx minus nu phi by x square. So, that is x dm1 dx. Then we had m1 minus m2. So, therefore, we will have plus d phi dx plus nu phi by x minus m2, which is again d phi by x plus nu times d phi dx plus Vx is equal to 0. Now, this we find finally dx d2 phi dx square plus d phi dx minus d phi by x plus Vx is equal to 0, which we can rewrite in the form d2 phi dx square plus 1 by x d phi dx minus phi by x square is equal to minus V by d. So, this is the equation of bending of plates, circular plates particularly with axisymmetric loading. So, if you now look into this, phi is nothing but, see herein the angle phi, we are considering the coordinates to be like this is x, this is z, and this is angle phi, and therefore, this is also angle phi, and in fact delta w delta x is going to be minus phi, because positive slope will be in this direction. So, then since this is phi is considered to be positive here, therefore, phi is nothing but minus dw dx. So, we have dw dx, and therefore, you see that deflection of the plate is given by this equation. So, we will consider further about this particular equation, and we will try to apply it to few cases and see how we can calculate the deflections and also the stresses.